Thank you very much, Arnaud. Can you hear me in the back? Looks okay. Thank you. Thank you very much. I'd like to start off by thanking the committee for having me here. I consider it an honor to be talking here to you. From the first moment I was very enthusiastic, and at this very moment I'm still enthusiastic, but to be honest, I'm also a bit nervous because it's going to be hard to meet the standards as set out yesterday by Professor Delicacios and Professor Torero in terms of knowledge and eloquence. But, well, I'll give it a shot and we'll see where it goes. So, well, Arnaud called my title a bit provocative. That is, in fact, also to keep your attention, because what I was going to talk about is how we can use computer modeling for fire and smoke dynamics in enclosures. And I'm going to ask the question, and that's the provocation, I guess, whether it's a help or a burden. So I would like to start off with a short overview by introducing a concept that I kind of invented on this occasion. It's available computing resources versus required computing resources. So I would first like to have some philosophical discussion, if you like, on this concept. And I'll briefly touch upon what could be the consequences in the context of fire safety systems design, but the main body of this talk will be about fire safety science and how numerical simulations, to my opinion, might help improve our knowledge in this interesting field. If I have time, I'll also briefly touch upon fire forecasting, and then obviously I'll try to end with some concluding remarks. Now, before saying what I will talk about, I first want to say a few things that I will not talk about, and not because they would not be interesting, but you have to make some choices. So I will not present a review of existing models in the state of the art of today. So if you were expecting that, I'm sorry to let you down, but this is not the contents of this talk. And I will also not talk about how you can assure quality of numerical simulations per se. That's also very important and very interesting, but this is not the issue of today. I will also restrict myself to the gas phase. So that means I will not say anything about pyrolysis modeling and only very few words on possible interaction of water with smoke and fire. So these things are very interesting, very relevant. Many of the talks here are on these topics. I'm well aware of that. But the story that I will tell is in a way generic. So it's not because I tell it in the context of gas phase that it would not apply to these domains either. Now, before you think this is going to be the shortest keynote ever, of course, I am going to address a few topics. So this is what I'll talk about, the gas phase simulations in these three domains. So as I promised, I would first like to introduce the concept of ACR versus RCR. RCR is the required computing resources. So this is what you need to have at least a chance of having an accurate and reliable simulation. So I'll touch upon a few aspects that might affect this required computing resource, and that's important to have an idea on what you actually need to do a good calculation. And then the question is the ACR, and it could be available computing resources, or if you don't want to use all that you have, it could be the applied computing resources, whether or not this is larger than the RCR. If not, then in fact, by definition, it doesn't need to be per se a bad calculation, but you cannot be sure that you will have a reliable calculation. If it is larger than RCR, then still you're not sure you're doing a good job. It's not because you use a lot of power that you're effectively tackling the problem that you want to solve. So the question that I would like to address, or maybe have some thoughts on how we might address in a systematic manner this inequality, is what are the consequences if we do not meet the RCR number. Now, I'd like to think a little bit back on what Professor Torero said in his summary of his talk yesterday. When talking about Professor Thomas' correlations, he stated that the limitations were clearly established. The assumptions were clearly established, and there was a clear research path outlined. Well, I think in numerical simulations, computer simulations these days, the developers know also very well what are the limitations, what are the assumptions behind the models applied in the simulations. But at the level of the user, this is, in general, I think, unfortunately, no longer guaranteed. And if they know, at least it's not always reported. And so this, I think, is quite an important issue, particularly for newcomers in the field, and that we must realize that there are a lot of assumptions underneath the blanket of that computer screen. So that there is a lot of things happening inside that computer. And there are limitations to any model that we are using. So I think it's quite important to know what are the limitations, and also if we are crossing the border of the limitation, how quickly does the quality of a simulation deteriorate. Maybe it's not that bad. I do not mean to sound too pessimistic, but it's just that I think we cannot say today that we have systematically analyzed the possible consequences of an ACR that is not larger than our RCR. Now, this is a sketch. So I'll talk you through this sketch. You see two axes. The vertical axis is the required computing resources. So you see, I have here a dashed dotted line, and then I label this the ACR. This is a line that is not at all static. In fact, that line is going up all the time as we speak. It's going up because we are helped by the hardware manufacturers, and so they're making the computers more and more powerful. But it's also helped by software developers who can make methods more efficient, that can give you more accuracy for a lower number of hardware. So this is a line that's going up, and this is good news, because we have more and more power to try and solve our problems. Now, on the horizontal axis, I have here three things. The first thing is called complexity, and complexity that could refer to many things. It could refer to geometric complexity. If you have a more complex geometry, you will need probably more resources to have a calculation in that complex geometry than when you have a simple geometry. I also have here accuracy. Accuracy could also mean many things, but one easy way of thinking about this could be, for example, in the context of a large eddy simulation. If you want more accuracy, one way of doing that is you choosing a finer grid. If you have a finer grid, you can expect, to a certain extent, also, in general, more accuracy. Now, if you want to improve accuracy, you're going on the right, or to the right of this axis, and you see that the required computing resources are increasing. The third aspect that I have here on the axis is the so-called modeling dimensionality. That's a difficult word, but what I mean there is that if you have more complex problems to solve, sometimes you also need more advanced modeling. To give an example, in smoke dynamics, if you have the question as to whether or not at a certain location in space, at a certain moment in time, you have smoke or not, so the binary question, yes or no, then you can treat smoke probably as hot air, give it a tracer, and check with a given fire source, and for example, also given venting or ventilation system, and you can see whether or not you have a tracer at a certain moment in time, at a certain point in physical space in a building, for example. But if you also want to know, for example, the concentration of carbon monoxide, well, then you will have to introduce some chemistry in your simulations, and then the modeling dimensionality increases. Now, it's a sketch, as I said, so it's definitely non-linear, but also you could have jumps. You could have jumps, discontinuous increases in required computing resources. For example, if you decide to include or not the activation of a sprinkler. If you have, at a certain moment in time, the activation of a sprinkler, all of a sudden you need to worry about the water, and you have a sudden increase in required computing resources. The full line here, that's just an addition of these three individual aspects. Now, it's a sketch, so it's just philosophical, if you like, but that's also because at least I am not in the position of giving numbers to this graph. And to a certain extent, I think this is a little bit our responsibility to try and find at least estimates of these numbers. So this is kind of a suggestion from my side, and well, I'm warning you, you will have a number of suggestions and opinions. It's not only going to be facts, so feel free to disagree. I will hear that during the questions. But a suggestion would be that we start to report systematically how long our calculations took on certain devices, so that we at least get some feeling as to whether or not we are working efficiently, but also towards the outer world, that they have an opinion, that they have an idea of how long a CFD calculation, for example, really takes. And so that People cannot get away with, for example, CFD calculations on very coarse meshes and trying to sell that as reliable CFD, because then you would see that the calculation simply did not take long enough. And so that's just one example. So I think that's a first suggestion of the day, if you like, is that it would be very handy for all of us to try and have some numbers, particularly on this axis, to know what is the required computing resources and computing time also for a given calculation. Okay, so what determines now the RCR? Well, you have to first define clearly and carefully the problem that you want to tackle. If you're not interested in species concentrations, then maybe it's not necessary to include too much chemistry. And so that's something that you need to decide beforehand. So once you define your problem and you have an estimate of the required computing resources, then you should set the ACR at least equal to the RCR. Only when you do that, you have a chance for success. It doesn't guarantee success, but at least you have a success. So just as an example, I think we can state reasonably comfortable way that today with a user-defined fire, and if you prescribe, for example, the soot yield and radiative loss fractions, and you do CFD calculations for smoke dynamics in a building, unless the geometry would be extremely complex, I think the CFD with state-of-the-art models can deal with such cases. So that means in the context of fire safety system design, we can state that the CFD can definitely help developing or assessing fire safety system designs. However, we need an investment, for example, in terms of the computational mesh. And that's quite an issue, because many, at least I'll talk for what I've seen myself, many of the systems design calculations are on computational meshes with LES, on meshes that are at least one, sometimes even two orders coarser than what you would expect from academic research. So why is that? Well, there is no technical reason, there is just a practical reason. If you have a coarser mesh, then you have faster results. So that means that time or money pressure is a driving force, say, towards coarser mesh calculations. So in other words, it is possible that ACR is lower than RCR. And then the questions arise, and how reliable do the results remain? Are they rubbish immediately? Probably not, but how strongly and how quickly do they deteriorate? That's quite an important question. If we do not have perfect calculations, do we at least capture the trends correctly? Can we say that today? And do we have an idea about safety margins? If we have a CFD result, for example, do we know what safety margin we need to apply? Is it 0? Is it 10%, 50%? And that's a question. And one of the things that makes life, I think, a bit more difficult in fire science is that the proof of the pudding is, unfortunately, not always in the eating. So it could be that somebody makes a design on a relatively low quality CFD calculation, that design gets approved, the system is placed accordingly, and it might happen that that system never has to operate. In fact, most systems never have to operate. So you do not know that maybe that system was a good system or not. You simply do not know. So that means that you do not learn quickly, or we as a community do not learn quickly from experience. And that's a difference from many other engineering fields, where you relatively quickly are confronted with the consequences of your own design. So that means that it's not so clear, at least not to me, what the answers are to these questions. And I think, and I'll come back to that later in this talk, that benchmarking studies might provide a very interesting insight in this matter. So this slide summarizes what I'd like to say about fire safety systems design. And I think we can say that state-of-the-art RCFD calculations. However, I do not mean to rule out zone modeling. On the contrary, I think a combination perhaps of CFD calculations in regions that really matter for accuracy and, for example, entrainment fire dynamics, and zone modeling in regions far away from the fire source where it's relatively easy flow fields could be a very valuable thing to do. In design calculations, I think we have to face, in the context of CFD, that we will keep on using user-defined fires in the foreseeable future, that we will not be in the position of calculating fire spread. And maybe it's not even that important in design calculations because often you do not know where the fuel is. And if you provide than the source terms, and you can question whether that is a valid assumption. I mean here source term in terms of heat release rate, obviously, but also in terms of soot yield and maybe radiation fraction, and that then you can calculate smoke concentrations in a reliable manner, because this is essentially a convection diffusion equation with a source term as a boundary. And we are there. I mean, that is quite okay. At the level of CO predictions, I think that's another story, because there is a lot of work going on, a lot of progress being made, but here we definitely have quite complex chemistry involved, and I also think that one of the next steps is going to be the true inclusion of interaction of water with, for example, smoke at the level of fire safety systems design calculations. So let's move on to fire safety science. And there I'd like to start off with a statement, and I hope that is not too provocative, is that CFD might be a very useful support for the development and further understanding also of fire theory. Then the question is, what route do we need to follow? And I remind you of this graph of a few minutes ago. If we have now this additional available computing resources, where do we invest it? Do we try to do more complex calculations, more complex geometries, more directly going on to interaction with sprinklers? Do we invest it in accuracy? Accuracy, for example, we could keep on refining computational meshes down to so-called direct numerical simulations. In a way, you could compare that, or you could see the similarity with using a camera with higher and higher resolution. And so looking at more and more details in the flow field. And we can learn from that, and we can look at detailed entrainment processes. So that could be a way to follow. Or do we go to more complex models, more higher dimensional models? And where do we put the effort, or where do we put the resources that we have? So, well, if you think about going to DNS, then you're actually trying to use the full potential of going down to the lowest level of the Navier-Stokes equations. And that could be a possibility. However, we must realize that, for example, in the turbulent combustion community, this is also being done. So I think personally that it could be very worthwhile to try and import as much knowledge as possible from other fields that are already doing part of our jobs. There is one exception, perhaps, and that is DNS calculations of low Reynolds number boundary layers in combination with heat and mass transfer. This is something that is, at least to the best of my knowledge, not intensively studied in the combustion community, because this is quite peculiar for fire, that many things are going on close to a wall. And the Reynolds number in fire is not very high. So these are things that we might want to consider doing some work on. So I think, closing down this discussion, to a good way of dealing with this ACR, RCR issue in terms of fire safety science, that benchmarking studies on cases that are relevant for fire would be a good idea to pursue. Now, this idea is not at all new, and there are already efforts ongoing, very valuable efforts, very fruitful efforts. And I want to name two. First one that I'd like to point at is the FDS verification and validation guide with a repository. And on the workshop session last Sunday, Kevin McGrattan pointed out that they have 44 sets of experiments available with more than 5,000 data points and that you can work towards, and we are all able to contribute to that. And so this is open to all of us sitting here. So if you want, we can try those experiments and see what's happening. Even more so, we can add new sets if we think there is a useful set of doing so. Now, the key target of this effort is, in fact, and correct me if I'm wrong later during the questions, to make the FDS code more fail-safe. So that is a clear benefit, because if it's more difficult to use it in a wrong way, then more people will use it in a correct way. So this is good in the process of progress in the future. However, if you look at the blog related to this FDS verification and validation guide, the response is reported to be disappointing, meaning that there is relatively little input from the community into that effort. And this is not criticism towards the initiative taker. On the contrary, it's something that we might want to reflect upon as a community. The second effort that I'd like to point out is the successful